Whatever, bro. We're probably on like 4 weeks of this unit. Hey, whatever, bro.
Okay, if you guys did not turn in the test review, I need that before we get started. If you had any late incomplete work, I need that before we get started. And you need to turn your phones and smartwatches to the side of the room before I get you your test to let you start. Alan. Alan's out today. Amelia's out today. School business today. A lot of school business.
For fun.
Jackson.
I almost was here and cried and learned so much. Last Sunday. Yeah.
All right, this is no document.
I've had a lot of people ask me that, but it actually got like slammed in a car door. Yeah.
So you've been chewing on it.
Yeah.
Just a bit of hair.
Is this the only page?
Yep, one page. All right, now remember this does add up to. Oh, sorry. Did I miss anybody? This does add up to 50 points, so more points than the quiz was worth. Also, these are major points. But I think we tried to structure it where you can get partial credit on most questions, except for question 1, since it's multiple choice. So that one will be right or wrong. Double check that you're happy with your answer on that one. The rest, you need to make sure you're showing me as many steps as you can. Try to show your thought process as much as possible, especially the last 6 questions because they're 6 points each. So if you're overly confident and then take a wrong path, you could lose 6 points pretty quick. Just make sure you're showing me what you can. Bless you. It is only 1 page. You don't need to feel rushed or anything. But once all the tests are in, of course, go ahead and grab your phones, and just wait patiently for everyone else to finish. And then we'll start to look at the handouts you picked up on the way in. So, but worry about the test first. Also, I'll give a reminder that just because you don't have a calculator to check some of your answers doesn't mean you could not check a few of them by hand. So you might consider doing that on some of the questions that it looks reasonable on.
You can give out partial choice.
Everything except for question 1, yeah. Also, there was one typo on here, but I don't think it matters, but just in case, just so it doesn't mess you up, if you have Form B in the top left of your test, it says test 3132. It's really test 3334. It has the wrong section numbers on there, but that doesn't really impact anything, but if that bugs you, then feel free to change it. That's only if you have Form B, though. looks like we've got all the tests in, so if you're working on something, I'll give you a minute to find a stop in place, and then we will start looking at the handouts you guys picked up on the way in. Okay, so our next unit is going to be much more direct and quicker, but it should be stuff that you're more familiar with. So you guys should have seen exponentials and logarithms in Algebra 2, but again, we know that you don't go super in depth on those, which is why we kind of take our time and really try to do it justice so that you have a good understanding of what's going on. But our next unit is going to be about 4 classes, and then we will have a test on it. I don't think it'll be a 50-point test. I think it'll be a little bit less than that. But we'll spend basically 1 day on linear, which is what we're about to talk about in a minute. So that's like mostly Algebra 1 stuff with a couple things sprinkled in that you probably haven't seen. About 1 day reviewing quadratics, what quadratic graphs look like, how to solve a quadratic, and a day on dealing with and reading piecewise functions, a 4th day to review, and then a 5th day to test. So again, this is a little bit quicker than our last couple weeks have been, but again, most of this should be familiar to you, but there are some things we have to sprinkle in so that you've seen them before calculus. So one of the handouts you picked up doesn't say, it just says review 1.1, that's going to be 109. And then one of them says worksheet 2, that'll be 110. So I'm going to walk you through 109, and then 110 is basically the same type of questions. It'll give you a chance to practice some of those. And then the extra practice is number 111. So that's where I just picked out the 3 question types that come up in worksheet 1 and 2 that give the students most issues, and so we can practice a couple more of those. But I don't know if we'll have time to look at all 3 of these today, but we'll get done what we can. And this is all the stuff that you need to know about linear. This is already, once we look at these 3, this is about 1/3 of what you should expect for your next test. All right, so the first little section talks about making an equation of a line. So there's a couple things you might want to jot down at the top of your page as we go through this. I'm really going to emphasize something called point slope form. I imagine that you saw this, but we pretty much live and die by this in calculus. Anytime we write an equation to a linear line, which is more often than you may think, we like to use point slope form. So it's the one that says y minus y1 is equal to the slope times x minus x1. So x1, y1 is the point given to you, and m is the slope given to you. So you really just replace the slope and the point. You replace 3 numbers, and then you have point slope form. Honestly, it's easier than the other one. So 99% of the time, if I have the option, I'm going to do point slope. There are a question or 2 in here, though, that specifically ask us for slope intercept form. This is the one that's going to sound more familiar to you. It's the mx plus b, where m is still the slope and b is the y-intercept. So if you know the y-intercept, then slope-intercept form is easy, but if you just have a point and a slope, point-slope form makes more sense. Now, through both of these, we're going to need to solve for m occasionally. So again, remember m is the variable that we use for slope. And you can find slope by counting rise over run if you have a graph. And if you don't have a graph, you should subtract the y values to calculate your rise, and then in the same pattern, subtract your x's to calculate your run. So, even if you're not choosing to do calculus next year, you guys can see this is all stuff that shows up on the ACT anyway, so it's a nice reminder with that stuff. Alright, so this is referring to 3 formats. So one format is point slope, one format is slope intercept. There is another form, which I probably won't even talk about. It's just kind of old-fashioned. It used to be more important. But general form is where you put the x's on one side and the y's on the same side, and you leave the constant on the other side. I think part of the reason we've kind of moved away from general form is in college it kind of varies greatly on what math teachers consider general form. Some math teachers, professors would consider this general form, some consider it this form, but A has to be positive. Some consider it A has to be positive 1 specifically, like you have to manipulate it. So I don't know. That's all just kind of preference stuff. So I'm pretty much going to stay away from this, but that's why it's saying 3 formats. I guess if you know that and you apply it correctly, then I wouldn't count it wrong. But okay, so we've got 4 questions here, and they want us to come up with the equation of a line. So let's just dive into question 1. So again, unless it tells me different, I'm going to try to do point slope. Point slope is the easiest. You can take any point plug in the x value for x1 minus a negative 1 becomes plus 1. You can plug in the y value in for y1, and then really the last thing from keeping you from having your answer is knowing what the slope is. So again, I guess you could sketch a graph, plot the 2 points, count rise over run, but it's a lot more efficient to just use the slope formula. Subtract the y values on the top, and then the same pattern, subtract the y values on the bottom. Now again, I don't know why you would want to do this, but just for the sake of argument here, if you were determined to put it in slope-intercept form, and I will admit, sometimes in calculus, like if they have a multiple choice question, they might do their answer this way, and then maybe the multiple choices in slope-intercept. But all you'd have to do, if you really wanted it in slope-intercept, is distribute the -3, and then add the 6 over. So it's pretty easy to change point slope into slope intercept. So point slope is just much nicer to deal with. If the y-intercept means something important, maybe slope intercept, but generally it's not the y-intercept. It's usually some random point that's important. Okay, well if we can do this for question 1, then we can skip to question 4, because question 4 also gives us 2 points, so we can do the exact same thing. I've got more than 1 point to pick from, so just pick one of them to be x1, y1. If you'd rather it be the second point, that's fine too. Just for consistency, I will just always pick the first point. But point slope looks like this. It's like a formula you need to memorize. 0 goes in place of x1, 5 goes in place of y1, and then the last mystery before you get your answer is trying to solve for the slope. That's the only thing that kind of slows me down for a second. So you can make a graph, plot the 2 points, count rise over run, or you could get out the slope formula. Subtract the y values over, subtract the x values in the same pattern. Looks like the slope is 5 over 2. Now technically, since this is -0, I guess I probably wouldn't leave it. I'd probably leave it there. And if for some reason you just insisted on slope intercept, you could add the 5 over, and then it would be an mx plus b format. But you only need to come up with 1 correct one, is fine. So that's how you would approach that 2 points. You got 2 options to find the slope. And then you just have to know where to plug the x value in and where to plug the y value in. You have to have this form memorized. Okay, back to question 2. We're going to need to know one other thing for this. So out to the side, you might want to write this if you don't remember this, but we need to remember the difference between a vertical and a horizontal line and a couple things about those. So a vertical line is straight up and down, whereas a horizontal line is left to right. A vertical line has an undefined slope. If you tried to take 2 points and do rise over run, you'd be trying to divide by 0 because it has no run. A horizontal line, if you picked out 2 points and did rise divided by run, you would get 0. There's no rise and there would be some run. 0 divided by anything would be 0. But you need to know that about those questions so that we can work question 2. So it doesn't say what form to put it in, so I would start off with this. Because it's horizontal, I know that he has a slope of 0. I don't know. I guess you can plug in -1 for x1, but it's going to be multiplied by 0 anyway, so it doesn't really matter. And in place of y1, plug in the y value. So I guess that's technically correct, but most of the time for vertical and horizontal lines, you might want to add one more thing to this. Horizontal lines will always end up having an equation that ends up being y equals a number, just like you see here. And a vertical line is always x equals a number. That's just the format of those. If you think about when we wrote the equation of vertical asymptotes earlier this year, it was always x equals something. When we did horizontal asymptotes, it was always y equals something. Now, you don't actually have to memorize those because you can just work it out the long way. That's what I did over here. But technically, if you know it's a horizontal line, the y values are always the same. To have this y value of 5 and to be in this format, it had to be y equals 5. So I don't know. I could probably go straight to this answer, but it also only took me 10 more seconds to just plug it in the other form. All right, and then question 3 is going to ask us to try to remember the differences with parallel and perpendicular. So you might want to jot those down to the side as well. Again, if you remember that really well, then I guess you can avoid that. But okay, what you need to know about parallel lines is just kind of generally what they look like and that the slopes are the same. Slopes are the same. For those lines to never touch, they have to be rising or falling at the exact same rate so that they can never touch. But perpendicular lines, which is what we need to remember for this guy, perpendicular lines intersect at right angles, and their slopes are what we call, well, there's a few different ways to say it. I say opposite reciprocals. So reciprocal just means flip your fraction over. Opposite means opposite signs. I know some math teachers say negative reciprocal, so you may have heard that. So when I look at, if I want them to be perpendicular to this line, I can see he has a slope of 4. It's right here, mx plus b. So since I want mine to be perpendicular, the slope I'm going to use is the opposite, positive 4, opposite would be negative, reciprocal. Instead of 4 over 1, 1 over 4. But then, as soon as I have a point and the slope, you can throw it in point slope. And again, if you know point slope form, it should take you about as long to finish the question as it takes you to write it down. Okay, so this would be a good This would be a good chance to, if there's any of these first four you want some clarification on. Any of that you want me to say again, or anything you had questions about? I'm guessing most of this sounds familiar. I'm guessing the only thing that's probably not super familiar is point slope form. Did y'all see that at all in Algebra 2? Huh? In geometry you saw it? Oh, okay. Again, you don't have to do point slope. I'm just saying it's a lot easier. It's less work, so yeah.
Why did you do plus in some of the equations for like the point slope form?
Like right here?
Yeah.
Well, so the form says do x, well, just like over here, the form says y minus y1. So if y1 was 6, it needs to be y minus 6. Over here it says x minus x1, so x minus a negative 1, because it was minus a negative, I just changed it to a plus. Okay, so that stuff should mostly be familiar to you. I don't think question 5 and 6 will be familiar to you. Not that these are difficult, but I don't think you're familiar with these terms. Most students don't learn these, or if you did, it would only if you took Honors Algebra 1 probably, and you probably barely talked about it. But these are some things that you just need to have heard before in case you're going to calculus, and that is direct variation. So direct variation, always, there's only a couple things you need to know. Direct variation always goes to the origin by definition, and instead of saying the slope is m, we usually use k, and k we call the constant of variation. So instead of asking you for slope, we might ask you for the constant of variation, but it's the same thing. So all you really have to know in question 5 is that direct variation goes to the origin, and it's just like questions 1 and 4 because you have 2 points. You could do the slope formula to see the slope is 3 over 2. And then you could either plug 0, 0 or 3, 2 in the point slope. Okay, now it's going to work. I plugged in 3 for x1, 2 for y1, and the slope in for m. And I got the slope because I had 2 points, so I could use the slope formula. But again, what I highlighted there, you have to know direct variation goes through the origin. That's just part of what direct variation is. Okay, number 6 will ask us to do some of the same stuff, but this one actually has 2 parts to this question. So they tell us this is direct variation. They want us to find the constant of variation, which we're going to call k, but it's really the same thing as slope. Just got a different term. So we need to find that for the first part of the question, then figure out what y is when x is negative 2. So they want us to do 2 things. Alright, well right here they give us a point. When x is this, y is that. Because they tell us it's constant of variation, we also know it goes through the origin. So if I need to know the slope, aka the constant of variation, I can just use the slope formula. Y minus y, x minus x, and then make sure you divide these by multiplying by the reciprocal. Looks like it would be negative 18. It's almost more just vocab for that first part than anything. Now, to figure out what y would be when x is negative 2, well, we can just make an equation. Honestly, that's what equation is trying to help you do. So I could plug in one of my points. I really don't want to plug in this point because I don't want to deal with more fractions than I have to. So I'm going to plug in this point. You can use either one you want to. Y minus y1 equals the slope times x minus x1. Simplifies very nicely. And I can see if I was to plug in -2 in for x, y would have to be 36. All right, so the keys to this question: constant of variation went through the origin. I had 2 points. Slope form gave me the constant of variation, because that's just the same thing as slope. Make the equation, plug in x equals -2, and you can solve for what y is when x equals -2. Okay, so until you get to worksheet 2 and the extra practice, that's all I've got for you right now on direct variation. Is there anything you'd like to clarify while this is still our topic? So again, you're going to have to practice that a little bit because you're not familiar with those terms, but notice the math that I'm doing is not really any different than the top of that page. You just have to know a few different things. Okay, on to the back page. We're going to do a couple graphs. We're going to change something to slope-intercept form, and then question 12, changing an absolute value into a piecewise function. That one will be definitely different than you've done in the past. But if I wanted to graph number 7, even if you had a calculator, by the way, you guys know that your calculator doesn't let you type in an equation like this. If you wanted to graph this in your calculator, you would need to solve this for y equals. So, subtract the 2x over, divide both sides by -3. That's what is equivalent that you could use your calculator on. But you don't need your calculator. This is in slope-intercept form, so I know the y-intercept. I can use rise over run with the slope to get a second point. And you really only need 2 points to determine a linear line. But if you want to count up 2, right 3, up 2, right 3, it might make your line a little bit more accurate. So basically, just put it in slope-intercept form, then you can see the slope, you can see the y-intercept. And then you can graph it. All right, question 8. This one can be a very quick question. If you remember that when it's x equals a number, it's going to be a vertical line, like we talked about on the other page. So the vertical line where x is always 4. If it was y equals 4, it would be the horizontal line where y was always 4. Okay, question 9. We're going to practice more of this type before your next test, because piecewise functions are just always kind of a challenge for students. But we can also start practicing them now so that you can think about them more than once. But I can't remember, have we done any piecewise function graphing this year?
I think so, like earlier in the year.
I'm trying to remember why we...
Not, I don't think you graphed, but piecewise we did.
Okay, I don't remember. Okay, but anyway, this one just happens to have 3 pieces. Piecewise functions can come in 2 pieces, 3 pieces, 4 pieces, etc. But 2 or 3 is going to be the most common. And the way I approach these is I just graph all 3 of these at once. So, some of the times it's y equals -4. I just graph the whole line temporarily. Some of the times it's 3x minus 2. That's mx plus b, so I know the y-intercept is -2. I can use the slope, rise over run. to get a second or more points. And sometimes it's y equals 2. Now, this is not my final answer. I still need to adjust this a little bit. But if you can graph y equals -4, horizontal line, y equals 2, horizontal line, and you can graph 3x minus 2, then you're almost finished. This is where, I don't know, students sometimes think these are difficult, but to me, I feel like it's telling you exactly what to do. Now, one thing I will point out to you that should help you see that this can't be the final answer is this implies that we're talking about a function, and to be a function, he has to pass the vertical line test. And what I currently have on my paper certainly does not pass the vertical line test. And the reason is I haven't used these restrictions yet. So sure, some of the times the graph is supposed to be y equals -4, but it's only when x is equal to -2, so that's a filled in circle, and less than -2, the stuff to the left. All the rest of it needs to go away. It's not supposed to exist. It's only supposed to be y equals -4 during those times. Likewise, it's only supposed to be y equals 3x minus 2 between these two values. When he's greater than -2, there's no equal to sign there, so that's an open circle. Open circle when it doesn't include it. And less than 1 do include 1, so that's a closed circle. So it's describing the x values between those, but not the x values to the left of -2 and not the x values to the right of +1. Just this piece, which is why it's called a piecewise function. Okay, and then finally, the last one was supposed to be y equals 2, but he should only exist that meets this requirement when x is greater than 1. So not equal to 1, that's open circle. Greater than 1 would be the stuff to the right, not the stuff to the left. So again, I just graphed these three, kept this part of this one, this part of this one, and this part of this one. And by the way, now if you look at my graph, he passes the vertical line test. He is a function, like his name implies. Passes the vertical line test. Even at x equals 1, it hits one time. It hits here, but not there. That's why we need closed circles versus open circles. Even at x equals -2, I know he hits here, but not here. Once again, it can only hit once. That's the need for the open circle, closed circle. So on the extra practice, I have a couple more of these to practice because I know that these often don't feel comfortable. But you just graph this, keep this part, graph this, keep this part, graph this, keep this part. And one slightly decent way to check is if it says it's a function, your answer better pass the vertical line test or you would know something's wrong. Okay, the last of our graphs. This is really kind of trying to feed into this last question 12, which is, I don't know, probably the hardest part of this. But there is a parent function, square root of x, that you should know what the graph looks like. He's the one that's the v. And then just apply normal transformation rules. You're going to subtract directly from x, it's going to shift it right 1. Still going to look like a v, but he's not going to go through the origin anymore. Okay, so 10-second recap of the graphing section. If it's linear and not in y equals form, you might want to solve it for y equals so that you can see the slope and see the y-intercept. Plot the y-intercept, use the slope. If it's a vertical or horizontal line, that can be a very quick question, but you need to recognize x equals a number is a vertical line, y equals a number, y equals a number, y equals a number is a horizontal line. If it's piecewise, graph all the pieces and then keep the parts of each one you're supposed to. Absolute value of x is a parent function that you need to have memorized, and then just apply whatever the normal transformation rule is. Okay, on to the last part, again, everything in worksheet 2 is just practice of this, and then the extra practice just focuses on the three types. So these are the last two new things in this. So this one says change the slope-intercept form. So again, even though I'm not a big fan of slope-intercept form, we also need to be able to work with it. So we need to get our answer into y equals mx plus b. But just like the first one that I graphed, that just means you're just solving for y. You're just trying to solve for y equals. So subtract the 2x over and divide both sides by -5. Then it's in mx plus b format. We can quickly see the slope. We can quickly see the y-intercept, if for some reason those were interesting. All right, the second part that I know you have probably not seen before, the first being the constant of variation, the direct variation questions, is you trying to make a piecewise function. So we're going to take this and we are going to try to make our own piecewise function that has two parts. Now, before I tell you how to do this question, I'm going to give you an easier version of this that should help you understand why these parts are set up the way they're set up. And this is the traditional one that normally gets asked, which is just a normal absolute value of x. We're going to not worry about the 3 and the -1 yet. If I wanted to make a piecewise function for just the absolute value of x, there's two different things going on here. This is like one of the lines, and this is one of the lines. That's how I know that there's two parts. So imagine this one, pretend like it just keeps going, even though it doesn't. What is the equation of this line? Y equals x, and he exists when x is greater than 0. What about this purple one? What's the equation of that line? Negative x, and he exists when x is less than 0. Now, this is a filled in circle here. He exists at x equals 0. So you can either include this or this, but not both, and not neither. It doesn't matter which one you give that point to, but it needs to go to one of them. That is the piecewise function that represents this. It's got two different line segments, but think about where these came from. One of these equations was the stuff under the absolute value, x, and one of these equations was the opposite of what was under the absolute value, negative x. So for us over here, I know if I subtract from x, it's going to bump it a little bit to the right. I'm just giving myself a little bit of a visual here, even though that's not accurate. So, what do you think the equation of this red line is? One more time?
X minus 1.
Close.
Plus 1. Well, 3x minus 1.
It's 3x minus 1. Think about over here. One of the equations was just the stuff under the absolute value sign. So over here, one of the equations is the stuff under the absolute value sign. Okay, what about this equation? How does this compare to this? That's okay, that's true too. But I was going for opposite. The other equation's the opposite of what's under the absolute value. So that would be negative 3x plus 1, the opposite. And that should make sense. Notice this one has a positive y-intercept, plus 1. This one, if it continued, would have a negative y-intercept. But then we have to think about this. This is a point of interest to us because it stops being the purple line and starts being the red line. Over here, it was obviously happening at 0. Here, I can't say so definitively. But what these both have in common is that this was occurring at y equals 0, and this is occurring at y equals 0. So if I set the equation, either one of these, that should give you the exact same thing, and plug in 0 for y, it tells me that this is changing from here to here at 1/3. But we need to be careful with the signs. My red line is when it's bigger than 1/3, and the purple line is when it's less than 1/3. So make sure you're pointing them the right way. And again, we need to make sure we actually hit this point, so we need to either include the point by including here or including there. Not both, doesn't matter which one, I will just alternate between them. But again, using this as a guide, one equation was what's under the absolute value, x, 3x minus 1. The other equation was the opposite of what's in the absolute value sign, negative x, negative 3x minus 1. This one changed hands at x equals 0. That's when it stops being this one and starts being this one. This one changed hands at x equals 1/3. It's when it stops being this one and starts being this one. I knew this was 1/3 because I knew y was 0 here, and I plugged in 0 for y and solved for x to see where that was happening. Yeah.
I just had a question about the graph. If you, the graph on the left, it looks like I see where the right one transformation is, but where does the 3x transformation kind of factor in? Because it looks like the only transformation was done was the right one. Does that kind of make sense?
Oh, okay. Are you talking about just like looking at this? What would the transformation be?
Yes, like how the 3x would factor in the transformation.
Yeah, so you would still say, if you were describing the transformations, you would still say this goes right one because of this. But then these rules, I don't know that we've even reviewed these this year, but it's kind of like if you go from x squared to 2x squared, if you multiply an entire parent function by a number, that is what's referred to as a vertical stretch or shrink, depending on if the number's bigger than 1 or less than 1. So this one's bigger than 1, so that would be a vertical stretch by a factor of 2. It makes it go up twice as fast. For horizontal stuff, that's when you put the number directly next to x. So this would be a horizontal, and the rules for stretch and shrink on horizontal are opposite the rules for stretch and shrink for vertical. So the fact that this is bigger than 1 means it's a shrink, and by how much is the reciprocal of that, 1/3. So even though this is like bumping it to the right one, it's horizontally shrinking it and shoving it towards the y-axis. It's making it 3 times closer to the y-axis. And that's great if you remember those transformation rules, but they're not anything you have to remember for this.
Okay, it's
Yeah.
not necessary for this, I guess.
No, because really the big mystery here, even with the quick little, like the fact that this goes to the right was enough for me to sketch it. Okay, I didn't know that this was x equals 1/3, but again, this is, 1/3 is not obvious, but it should be obvious that y equals 0. So just plug in 0 for y and solve, and don't, it'd be risky to try to do it with the vertical and horizontal stretches and shrinks and stuff, unless you just remember those rules. So again, this is a type that you will need to practice more of, but I know there's one on worksheet 2, but I've got 2 more on the extra practice. So if you guys would take a couple minutes here, and if you would go ahead and start worksheet 2. If you do just a couple questions on it, that will be enough. You don't need to do any of this for homework. We'll talk about it a little bit more next class before we move on to quadratics. But again, worksheet 2 is just like worksheet 1, except for 1 and 2. 1 and 2 didn't show up on worksheet 1, but this should kind of help you identify what things stuck with you and what things you still remember and which things you don't. So again, put a couple minutes into it because you still got about 7 minutes before you're gone. But don't worry about doing any of it for homework right now.